So the job that you just saw me doing here was that I have around 0.5 gigabytes of input files, which are textbooks, and I have implementation of MapReduce based on Google's 2004 paper that I've done myself, which take every single word that happens across all of these text files and index them, search for that word and find out in which one of these text files it appeared. And here I can give an example. Air appeared in these files and hello appear in this. So what I'm going to do in this video is to spell the whole things out. I'm going to explain what MapReduce really is, what problem it solves, how to implement it, and what's the implementation look like in a distributed system. So it operates in a cluster of computers as a master and a bunch of workers. So let's start with a bit of history to understand what problem this MapReduce actually solves. So around 2004, Google was scrapping the entire web, and they have to drive some sort of computation from this pile of raw data. For example, they have to understand which page link which, or they get the index of the words in the pages, or understand what are the most query pages per day. So each one of these computation on its own, like counting the number of the words in all of these web pages, or grouping them together, or inverting the list of them to get the reverse index, on its own was fairly simple to code. But the problem was that the size of data was so big, and if they wanted to execute the computation on a single machine, they'll be limited by the resources of the single machine. From any of this computation, they had to sometimes split this supermassive data into multiple pieces and distribute them into the multiple computers, like hundreds or sometimes thousands of machines, do the same computation on each of those machines individually, and then sort of get the results and reduce them down or accumulate all of the results into a final output. As soon as you move the computation to multiple machines, you have to add extra logic and complexity to your code to, besides the computation, deal with some other things. For example, scheduling and tracking on which one of this machine, which part of your data being computed, or splitting the initial input, shuffling and sorting. And if you've been running this job on hundreds of computers, there are always jobs that are failing and machines that are dying. There need to be logic in place to retry these jobs. So that's what I'm trying to convey with the top part of this diagram, that despite the computing logic itself, like counting, grouping, and inverting, was simple, but the fact that they had to run it on multiple machines, meaning that they had to add complexity for any of this computation besides the actual computing logic. So they ended up in a situation that for every single of these computations, they had to add an extra layer of plumbing to the code. And many of these engineers who've been working at Google at that time been experts of things like clustering or crawling, but not necessarily expert in distributed systems. But they ended up by basically writing the same layer of plumbing besides the computation in many places. So the rational move here would be to extract this layer of plumbing as a framework and expose an interface where people can just implement the computation logic that concern with the actual results that they trying to drive from a data, and not have to concern with the complexity that comes with the fact that this entire computation need to be executed on a cluster of machines. And that's exactly what Google did. They took this idea of map and reduce functions from functional programming, and turns out you can compute a lot of things using only these two functions. And they built this framework, which they call MapReduce, where as an input accept these two functions, which are basically coded by the engineers, experts in that field. And the framework will take care of the pieces, the plumbing layer, for example, splitting the input, the scheduling and tracking of where this function, on which machines this function is executing, shuffling and sorting the data, and retrying the dead jobs. And that is what is visible here on the bottom part of this diagram. What are these two functions that you plug in? Let's take a look at them. So to understand how map and reduce function are used to perform such a computation, let's walk through a simple example where, given a number of input files, we want to extract the count of every single word that happened across all of these files. For example, in this case, in example that you see on the screen, we have two input files, a.txt and b.txt, and each one includes 3 words. And we want to get to the output on the right hand side where you see the number of each word is noted in front of the word itself. So the first stage would be to feed every one of this input file into a separate map function, where that map function will iterate every single word in that input file that it fed and will output a pair of the word and number 1, meaning that that word was seen once in that input file. So for example, over here, a.txt was provided to this map function on the top, and as an output, we get this list of word and number pairs, and the map function cannot see the input of the other map function. So over here, the map function on the top only see a.txt, and the one on the bottom only will need to reach out. So the next step is shuffling. You get the output of all of the map functions and group the output by word. For example, in this case, we have the word the, 1, 1. One of the outputs coming from the map function on the top, and the second one coming from the bottom, visible by this yellow line. The cats group only coming from the output on the top. The word sats coming from both outputs of the top and bottom. So we have sat 1, 1. And the last stage is to then feed every single one of these shuffle groups into a reduce function where it produces the final results. Where in this case, the reduce function is basically sum of all of the values. So as a result, we get the 2, which is sum of 1 and 1, cat 1, sat 2, and so on. So as you just saw, by following this 3-stage process of map, shuffle, and reduce, we were able to get from the input to the output that we wanted. The end user needs to only implement the map and reduce functions, and this is the MapReduce frameworks that take care of everything else, which is splitting the input and fitting them into the map functions, then shuffling the data and fitting this intermediate output to the reduce and getting the results and writing it to some sort of storage, and also retrying some of these functions that might be failing. And now to prove this concept, let's try to implement the map and reduce function for this word counter and trying to use it into a simple sequential MapReduce program to get the results. So here I am in a fresh Go project that I just created, a module that I just named Tiny MapReduce, and I'm going to share the link to the GitHub repository in the description of this video. And we're going to start off by defining the map and reduce function for the word counter that I just presented. So I'm just going to create a file and name it word counter functions go function package main, and so the function map. So remember that map function will receive an input file, and for the word counter it needs to iterate over every single word and return a pair of word and value or 1. So we're going to need to define output type, which I'm going to call keyval maybe, and so basically have a key, string, and value, which is also in a string. So the map function will receive a file name, which is a string, and the content of the file, which is also type a string, and return a list of these key values. So we're gonna need to start off by extracting all of the words from the content, but a content, let's say an English content of a textbook, includes a lot of things other than letters, like punctuations, exclamation mark or comma or colon. So we need to filter out those things, and for that reason I'm going to use the field function of the strings package, which allow me to provide it with filter function, which I'm going to just pass here as the anonymous function, which basically iterates over every single character, and we're going to filter out the ones that are not letters, which we can use the Unicode is letter and just pass it this, the character here. So we're gonna get the list of the words here, which are actually words, and then initialize the key value response that we want to return, which is the key val. And then we need to iterate over every single word. So basically, we don't need the index for word in range of the words. And then we have to basically append every word to the key value response with the key of the word and value of 1. So it's going to be, yeah, append of this, create key here would be the val, would be number 1. And at the end, we're going to return the key value response. So this will be our map function. And for the reduce function, which I'm going to implement here on the bottom of this file. So for the reduce function, remember, we're basically going to, after we get the map function results and we shuffle and we group the values by key, the reduce function is going to just sort of sum up all of these values in case of word count. So basically, let's say given the key and the values, which are basically a list. In this case, let's say for the word hello, you get hello 1 1 1 1. So what you want to do, you want to return the length of these values. But because we want to return a string, we need to use integer to string converters, which is coming from string com.I to a. Yeah. And this is how reduce function looks like. And again, to recap, giving a key, for example, in our previous example, it was the word sat, and the values, which are basically the result of grouping from the shuffling, which was 1 1. All reduce need to do is basically sum all of these values, which are in this case is, imagine we have values 1 1, which are two strings, and we want to get the length, or in other words, how many of these ones are found, and we're just converting it using the string converts I to a, because otherwise if you try to use, let's say, a string type here in Go will return the ASCII code for that number here, and that's not what we're looking for. We're looking for the actual number just turned into a string. So, and to demonstrate how the results of this map and reduce look like, let's just try to reproduce the diagram, the input from the diagram that I just showed. So I just create a directory, call it in, and I'm going to create an a.txt. I'm going to write the same thing, the cat sat, and I'm going to create another text file. So these are our input files. So we get the dog sat. So we have these two input files. Right, now let's go ahead and create another file, which is going to be our sequential MapReduce implementation that we're going to invoke the word counter map and reduce from there. So I'm just going to call it MapReduce simple go, and it's going to be the main function. Okay, so for this sequential MapReduce, I want to be able to provide the input files as an argument to the program. So let's start by doing a little bit of argument checking. So if number of the arguments is less than 2, I would like to basically throw an error and exit. So I'm just gonna say, I'm gonna write to the standard output, standard error that a usage is, simple. You need to provide the same input by 1, and other input files are optional. And I'm just gonna exit here. We need to read every single one of these input files and fit them individually to the map function that we just defined. So that's what I'm going to do. So I'm going to say for each one of these file names, so that's coming from the arguments to this program. So what I need to do, I'm going to open the input file. So it's going to be os. And if you run into error, I think we want to just exit the program. So I'm just going to say cannot open. It's going to provide the file name and the error. And so what we want to do, then we want to read the content. So input content going to be, we're going to read the entire content in the memory. It's error. We want to make sure that we close the input file here, because we read the content and we don't need to keep the file open. Send this function to send the content and also file name to the map. And because I named these other files word counter functions in the same namespace, the map is going to just point to this. So I need to provide that with the file name and input content, which we're going to need to turn into string because this is bytes. So the result of this is going to be a list of key value pairs that we have to then store in some intermediate place that we can then shuffle, group them in a shuffle. So I'm going to just create intermediate key val, which is going to be key val. And again, this key val coming from this other type that we define in this file. And what I'm going to do is I'm going to do appending to the results of this. So we have the intermediate key vals, which is basically a flat list of these key values, because here I'm just basically spreading this list. Right, so the next step here would be basically shuffling, where we want to get the similar keys, or in this case word, and put them in the same group. And shuffling here is basically we can use sort, because if we sort this intermediate key value based on the keys, the words that are similar will end up next to each other in the slice, and then in the next stage basically treat them as a group. I'm just going to run a sort on the intermediate key value based on the key, and for that we can use the sort func from slices package, which given a slice, we can provide it with a sort function, which gets A and B here, which are both key vals. If we want to compare A and B and return a value either -1, 0, and 1, and A and B are basically two elements of inside this star, which we need to compare to each other. Based on the value they return, it determines if A need to be before B or B need to be before A, or they need to be in the same place as they are. So I'm going to just use the compare based on the key. Right. And so this sort func basically modify this intermediate key value. So we're going to end up as the results here with something like this. We have a slice and we have key, let's say hello values 1, and if we have another key here, hello, it's going to end up next to this. And if you have like a key, let's say by, this is gonna be basically be next to another by key, and then we can treat them as a group to provide them to the reduce function. So let's go ahead and do that. And so I'm basically going to create an output file which will output the results of the reduce functions to it. So I'm just going to call it, use the OS create here, and I'm going to call it out, or word counter out. So yeah, and like I said, we have this intermediate key value sorted. To be able to feed the similar keys that we sorted here as a group to the reduce functions, I'm gonna define two indices, I and J, and I'm gonna move these indices in the slice until the key are the same. Feed it to the reduce function, write it to the output file that we generated, and then move the I index to the next to J. So let's go ahead and do that. The I index will start from 0, and we're gonna continue until the I is less than the length of our the key value, the intermediate key value. So the J is going to be the next element, so it's going to be I plus 1, and until J is less than the length of our intermediate key. So here we're trying to basically find until which element the keys are the same. So basically intermediate key I key equals to intermediate key val J the key. We want to continue increasing J, and right, once we have I and J, which are I is a pointer to the first key and the J is to the pointer to the last key, and the keys are similar. What we want to do, we want to put all of the values that are associated with these keys in the same group. So I'm just going to create a slice of integers, which I'm going to call values. And what I'm going to do, I'm going to go from I to J. So it's going to be, I'm going to create another index. I'm going to call it K, which is until K is less than J and K++. And we want to append the value of that K, intermediate key dot K dot value. We have all of the values grouped in the same slice. And once we have the group, we want to feed it to the reduce function. So I'm going to just call the reduce, and again, it's going to point to the other file. I'm going to provide it with a key, which is basically, we can use either I or J for the key. So I'm going to say intermediate key I.key. That's the first argument, and the second argument is basically values, and we're going to get the output. Let's say this is reduce out. Right, then we want to basically write this output to our output file that we just created. So I'm going to say fprintf to the output file, and I'm gonna write it as a key space value next line. So it's going to be value next line. The first one is going to be, it's going to just break this down to it's visible, right? So the first one again is going to be the key, so I'm just going to use, and the second one is going to be the reduce output. And then we want to move we want to index this to the j. We want to move the I index to the j. I forgot to handle error here. So when we create an output file, if there was error, we want to fatal out and say, yeah, cannot create. I'm just going to print out the error. We have to remember to close the output file. So I'm just going to use file close differ, which will be executed at the end of this function, end of the main function. Okay, so to quickly, we created two input files. We have our map and reduce function put together here. Reading the input files as an argument. What I'm doing is creating the intermediate key value sets, which is the result of the map, feeding every single one of these input files into one round of map function. And then what I'm going to do is I'm doing the shuffling, which is in this case just sorting to get the keys that are similar next to each other, create an output file, and then using this logic over here, I will have the values of the same keys in a group fed into the reduce function, getting the outputs and writing to the output file that we created in this format. So let's go ahead and run the program. So I'm going to just provide it with all of the text file that we have in the input folder, which is A and B. So it seems like we have infinite loop, which should be here. So yeah, here I'm supposed to break from the loop if the keys are not similar, because otherwise it will stuck in this loop and it will never increase to hit this limit. So I'm just gonna break from this loop, or we could also take this and put it as an and here, but this should be good enough. So let's try to rerun the program again. So we have a word counter out, and yeah, as you can see, the result is exactly what we saw in the diagram. We have two sats, and two for cat and dog, it's only one. So in this simple MapReduce implementation, we have the map and reduce functions implementation sort of embedded in the same package. So before we go ahead and implement MapReduce framework in a distributed manner, let's make small improvements so we'll be able to provide this map and reduce as a plugin to our MapReduce framework. We can achieve this is to build these functions as in a plugin mode, and we can do that by running go build mode plugin. The output could be work counter .so of work counter functions.go. So this is the flag. Build mode is the flag. So now that we have this shared object, I want to be able to provide it to our simple MapReduce as an argument. So it loads it as a plugin and extract the map and reduce function from it. Something like this. So I'm going to say go run MapReduce. We'll provide it with the work counter shared object as an input all of the text files. For this to work, we need to make some adjustment to our MapReduce. So first of all, I'm gonna increase the number of these arguments and add to the usage that here you have to provide a function plugin. And here I'm going to just get the map and reduce functions from a utility that we implement. So I'm just going to say, I'm going to create this utility. It's creating a folder, utils.go, maybe package util. I'm going to call this, let's say, load plugin. So yeah, as an input, this is going to return a file name, which is going to be the file name of the plugin that includes the map and reduce function. And it's going to return basically our functions, which are going to look like a function for the map where we accept the file name and the content, and we return a slice of key value. And it's also a good time to extract this key value that we define in our work counter functions and move it to the utility. And the reduce function that I'm going to return is basically also receiving the key, and basically key value pairs coming from the map and returning list of a string. Right, so let's quickly also fix this key value. And I think we can fix it just by, so I'm gonna import our util that we just defined. So the name of the module is tiny MapReduce utils, and I'm just gonna prefix this with utils. Right, so let's get back to our utils and define our load funcs plugin. So for this, we're gonna just use the Go plugin package. So we're gonna start by opening up the plugin from the file name that provided. Yeah, basically gonna return an error here, or let's just, I mean, you're not usually killing the program from a package, but let's just do it anyway here, right? So I'm gonna look for MapReduce funcs. Running an error, we're gonna look up for a function called map and to do some error handling here. So if we found the map func, we're gonna cast it to the type, and we can do that. Basically just copying this type over here. We're gonna repeat the same thing for the reduce, but we're just gonna look for reduce here. But the type, the type of the reduce functions is of course different. So we're gonna cast it to this type, and I'm just gonna simply return the map function and the reduce function. Okay, so we'll be using this load functions plugin in also our distributed MapReduce framework. So this is basically, to recap, it's loading a Go file that we just built as a shared object, as a plugin. Look for map and reduce function, cast them to the file, to the types that we are originally defined for our map and reduce function, and just returning those functions here. So let's go and use this. So I'm going to use the utils dot load funcs, and so this is going to be the second argument. Right, yeah, this key val here gonna come from utils as well, same as here. And here, instead of calling the map reduce, so here, instead of calling the map directly from the other file, we'll call this map function that we read from the using this plugin, and the reduce function that we just gonna also fix this to map func, and reduce function over here. So the reduce function coming from here, right? Yeah, this could be a list of strings basically. So we only need to provide it with the values in that we group. I mistakenly put the key value array slice here. I want a small error here. Reduce is supposed to return a string. Remember, reduce gets a group of values or a list of values and basically reduce them down to one value, which is stringified number. So if we try to now build our program, build the shared object, the functions again, run the program with this command that we provide the shared object that we just built, it should produce. And the reason for this is probably that the input file that's now stored from the index 0. Remember, so it was basically reading the shared objects as an input, but it still work and still count all of the characters, all of the words there, but it's not the set of input that we want to provide it. We wanted to provide it with basically second argument onwards. So let's retry to be much faster, and yeah, we get the same results. And now basically we have an interface where we can plug in our functions as an argument. Now that we have this fundamental understanding of a MapReduce, let's go and design a MapReduce that operates as a distributed system. Okay, so we're going to implement this distributed MapReduce with two separate processes, a master process and a set of worker processes. So the master process is going to be basically the brain, where it's coordinating the task between the workers, and by task I mean map and reduce tasks, and keep track of the state of those tasks. So whether those tasks are in progress or completed or not scheduled. And we're going to have master and workers to communicate with each other over some sort of RPC. In our implementation, we're gonna be running both processes on the same machine. So we're gonna have local sockets, have workers and master talking to each other over the sockets. And the reason that we want to separate the master from the workers and have the task state on the master is that will allow us to dispose workers at any point and replace them with another worker. And that means that the data that workers are holding at any moment are never going to be irreplaceable. So we can easily swap the workers or schedule that task on another worker and calculate that data again. And this design choice will allow us to survive from the failures later on in our implementation. Right, after that, we want to start by defining two variables, M and R, where M is the number of the map task and R is the number of the reduce tasks. And also M determines to how many pieces we want to chop our initial input files. So in this case, we have M16. So if we have 16 input files, we're going to run each one of those input files in one map tasks. But if let's say we have 8 input files and we have M defined as 16, then we need to chop each one of those input files into 2 pieces. So we can run each one of those independent input pieces into a map tasks. And also reduce task is going to be the number of our final output files. So remember, our final output is result of the reduced tasks. So in this case, having 4 reduced tasks by setting the R to 4, meaning we're going to end up with 4 output file. Next, we want to fit our input files into the master, because master is the starting point where it defines those map and reduce tasks, store them in a state, and then schedule them on the workers. So let's say in this case, we have a list of input files, which are 4 that we feed into the master. So then this master process is going to create the map and reduce task from the input files that we provided based on the variable M and R that we specified. So in this case, we specified M as 16, meaning that we have to create 16 map tasks. So let's say here we have 4 input files. We have to somehow create 16 tasks out of that. So one way would be to split each one of these 4 input files into 4 pieces. So we have 4 times 4, 16, and each piece is going to run in a separate map tasks. And one easy way to achieve that without actually splitting the file into a smaller file is to just use the pointers to the character inside the file. So let's say each one of these input files is 100 character. So we need to split that into 4 pieces, and 100 divided by 4 is 25. So the first split gonna start from the character 1 to character 25. The second split gonna be from the character 25 to 50, and so on and so forth. And that way we're gonna have just small pointers stored in a memory rather than, the entire data being loaded into memory. So each one of these tasks also gonna have a status. So we're gonna have a status idle, meaning the task is not scheduled on any worker yet. And we're gonna have a schedule in progress, meaning it's scheduled on a worker and is running. And we're gonna have a status done, meaning the task was completed. Likewise, we want to master defines the reduce task based on the number R that we specified. Over here, we have 4. So we're gonna simply just define R0 to R3 and a status specified for each task. So, and the reason to define these statuses is that this is how master can then later on determines if the task is failed. So for example, if a task is in progress for a long time, based on a timeout that we can define, the master can change the status of that task to idle and try to reschedule that on another worker. Right, so at the next step, workers are going to reach out to master over the remote procedure call channel and ask for a task, and master are going to pick any map task that is available, is idle, and schedule that on that, give it to that worker. and then change the status of the task to in progress, and also store the worker ID which running that tasks. The reason that you won't have the workers to pull the data from pull the task from the master rather than master reaching out to workers and giving their task is because, let's say, on a real world distributed setup, you're going to have hundreds or thousands of workers, and having master to reach to all of these workers in some sort of loop, it's not really going to be practical, because let's say if any of these workers are slow and can't respond in a specified time frame, or if any of these workers are dead, masters still have to reach out to them and wait for the responses. And so we're going to have to implement some sort of failure detection and dealing with those failure logic in the master. So we can just simply skip implementing that logic by having workers to pull from a master, because if the worker dies, it's never going to ask for the task, and if they're slow, they're going to ask with a much less frequency. So the happy path is being taken care of automatically. So at the next stage, the worker will read that byte slice that master provided from the inputs and run it through the map function that it was loaded to it on a startup. And as a result, like we saw in our sequential MapReduce, it will spit out slice of key value pairs, and it will write those key value pairs to its own local disk. So the data remains on the worker itself. And the way that it will write it to that local disk is that, so it will first of all split the local disk into multiple partitions, which the number of the partition is equivalent to the. So in this case, we're going to have 4 partition on the worker disk, and then it will calculate the hash of the key of each one of those key value pairs modulus R, where again R is the number of reduced tasks, and it will land in one of those partitions. And running the same key in this calculation will guarantee that that key will always land in one specific partition on a local disk. And then we will later see what will be the use case of that. So 2 things to point out here is, first of all, these keys are sorted before written to these partitions. So later on in merging that we're going to do in reduce is going to be cheaper. So that's one small optimization. And second of all, we want to periodically, as we calculate these key value pairs, we want to flush them to the disk. And we want to stream these inputs into the map function rather than reading the entire thing in the memory. And that will help us to save some of the memory space. So after this key value pair list returned from a map function running on a worker was stored on local disk of the worker then will send an RPC call to the master and report that this map task that was assigned to it was completed, and also provide the location of this intermediate key value pair file on its local disk, and then master updates the state of that task in its store. And benefit of having this intermediate key value pair stored on a local disk is that we're not passing data over RPC to the master, which is expensive to move the data over the network. And instead, we just have a couple of bytes pointing to the local disk. And having this data on the local disk is completely fine, because at any point of time, we can again run this map on another worker and get the same result. So this same process of running the map functions on these workers need to continue until all of the map functions are finished and the intermediate key value pairs are stored on these local disks. And the reason that we have to wait until all of these map tasks are finished before moving to reduce task is that the reduce task, remember, for example, in case of our workout example, they need the result from all of the map to be able to calculate the correct count of the words. So let's say if we want to calculate the number of the words there on all of these 4 input files, which we split it into 16, we have to make sure that we have the extracted from all of these 16 splits before we go ahead and run it in a reduce function. All of these map tasks need to be assigned to to the workers, and workers need to calculate this key value per list. They're going to write it to the local disk to a specific partition based on the R, and they're going to report back to the master that that task was completed with a pointer to the location of that intermediate key value pair on their disk. Only after all of the map task was completed, we will move to the reduce. So now that we have all of the map tasks completed with the address to the partition on the local disk, we can calculate for each one of these reduce tasks from which partition on which worker the intermediate key value pair must be pulled before running in the reduce function. So the same procedure is going to happen, and these workers again going to ask for if there are any task available, and then master is going to check that, okay, now that all of the map tasks are completed, I'm going to pass out one of these reduce tasks. So in this case, reduce task 2, or the third one in the list, was passed to the worker 4 with the information of that you need to read the partition number 3 from these specific workers. So what the worker 4 will do, it will reach out to the workers that are passable in the reduce task to it directly or with the RPC and ask for intermediate key value pairs list from that specific partition. So now it should be clear that why we, after calculating this key value pair, we have to run in this formula of modulus R and write it to that specific partition, because later on this another worker that will be assigned that reduce function, reach out to the worker that have that intermediate key value pair and ask it to give all of the keys that are available in that specific partition, and need to do that for all of those workers. So now you can also see another benefit of having this data store on the local disk of the workers, that we're not going to have the bottleneck of only having this data on a master and all this traffic need to go to master to pull these intermediate keys, and instead this traffic will be sort of run across the entire cluster and the load will be balanced more evenly. So after this worker pulled all of the key value pairs that are assigned to the partition that associates with the reduce number, that's reduce number of the task that it picked up, it needs to then merge all of these key value pairs together to again form those groups before running it in a reduce function. So this is literally the shuffling part that we did with the word count that we use sorting to have the keys next to each other. And remember that I quickly pointed out that after running the input in a map before writing it to the disk, we will do a local sort. It should be somewhat cheaper here to merge these sorted keys now, and we can use something like KV merge or minimum heap to just merge all of this result and get big sorted list of the result of all of these partitions. And with having that list, then we can run all of the values of each key. We can pass it to the reduce function, get the result, and write the output to some sort of output file, which is going to be outside of the worker here. And again, remember, each reduce task is going to produce one output file. So there's going to be 3 main failure recovery mechanisms that we need to put in place. First of all, we need a way to recognize the tasks that are failing, and for that we're going to define a fixed number for the timeouts, x number of the seconds, and as soon as we assign any of these map or reduce tasks to any of the workers, we're going to start the timer, and if they fail to deliver that task within that timer, we're going to change the status of that task to idle and wait for a worker to reach out and assign that task to another worker. So let's say in that case, one of the workers pick up the task and it took a bit longer for some reason. I don't know, worker was slow or something. And we set that task to idle, and the second worker pick up the task and completed that and write the results back to the master. So by writing the result back, I mean they reported that it was done, and we have the location on that the worker number 2 that the intermediate keys, let's say for the map, are stored. So if the worker 1 that was delayed now reach out and try to set the result as done, master gonna simply ignore that. We're just gonna reject that request. Another thing for the reduce task, remember I said that we will, after running the reduce function, we're going to write the result to some sort of outside the storage. So in this case, it's going to, let's say, it's going to be our because all of this was worker and master processor running on the same local machine, they're gonna be writing this file to the same file address. So if the reduce, so let's say one of these workers pick up the reduce task, and again it delays, and another reduce picks up the same reduce task, and it open up that file and trying to write to it, and the delayed worker also try to open the same file and write to it. We're gonna end up with a corrupted data because they're gonna write to the same file. So, and dealing with this, in our case, we're gonna just use a temporary file. We're gonna just create a temporary file and then use as rename, which will be take care of this race condition for us. So to finish up this, we have to wait until all of the reduce task was completed and report back done. And after that, let's say master process will exit, or worker processes will exit as well. And the way that they can determine when to exit would be when they're asking for work. If master failed, let's say after X number of the calls, they will just exit. So very quick recap. We started by saying that we're going to have master and worker processes. We're going to have M number of the map task, R number of the reduce task. I start by splitting the data into map task. The workers going to reach out and ask for the map task, and they're going to read the data from the file, from the offset that's specified and the length that is specified, run it against the map function and write it to the partition number that they calculated as a result of running the key in a hash and calculating the modulus by R. And we're going to have the same story, but the number of the R for the reduce task, and then reduce is going to reach out to that worker that have the data on their local disk, pull it, do a shuffling on it, which is literally merging these sorted keys together, and then running those values in a reduce, and alongside the key writing to the output. We discussed about dealing with the failures and how we can prevent from corrupting the output files. And now with the understanding of this, let's go ahead and start implementing our distributed MapReduce. Okay, back to our tiny MapReduce project. Let's just start off by defining the master process. So I'm just going to create a new file here and call it MapReduce.go. This is going to be our master, right? So let's start off by creating the master struct. And remember, this is master that keep track of the map and reduce tasks. So we're going to be storing those map and reduce tasks here. So let's first of all define the task. And because moving forward, we're going to share a lot of these types between master and worker, let's define it as a part of our utils package, so we can share it between both of them. So I'm going to create an rpc.go, and I'm going to create task type. So now let's think, what are the things that we need to put in a task? So obviously task needs to have an ID. When we are assigning a task to a worker, we need to have the worker ID here. I'm going to use integer for the IDs. So a task going to have a status. So we're going to need to define a status, and let's represent the task statuses by integers. So I'm just going to define constant. So we're going to have idle, in progress, and done statuses. And we're going to be using the task status here. So a task could be either map or reduce. So let's define function type here. I'll call it a task function type, and I'm going to define it right over here. No, we're going to need to do the same thing here. So either going to be a map function or it's going to be a reduce function. So if it's a map task, it's going to need to read the data from some sort of input. So let's keep track of the input address in the task. So it's going to be in a string, which is a path to the input. And remember about splitting the input. So we're going to need to, for the map task, have a starting offset of our input split and the length of the input string. So I'm going to have input offset as 64 integer and input length as same size. And also we need to keep track of when this task is started. So we can change the status if the task wasn't finished in the timeout that we'll define later on. So I'm going to have an started at, and it's going to be of the type time, right? So when we get the output from the map, which is going to be a key value pairs list. We're going to need to store the address on where that output is stored on the worker local disk. So I'm going to do map outputs, which is going to be a list of the map output. We're going to define that type over here, which is going to be again address. This is again address on where this output is defined on the local disk of the worker, and the size, which we're going to keep track of for metadata. So this is structs. Right. So now let's go back to our MapReduce master. So like I said, we're going to have the map tasks here, which is going to be a slice of utils task. It's going to be a pointer to them. And we're going to have the same thing, but for reduce tasks. And to fix this error, I forgot to name this RPC file that we created. We need to name it the utils package. Right. And of course, both of these are integer. Okay. So we have the master structs that's storing the both map and reduce task as a slice of the tasks. So when we triggering the master, we accept the input files for the MapReduce as provided. So we need to do a bit of validation here. If that was less than 2, then we want to just basically error out stun.error, and we say that the usage is MapReduce master, and you're going to need to provide the input file and exit 1. So this is fprintf. Right, this should be outside. It's the length of the comparison here. So let's create a function to initialize the master. I'm going to call it new master, and this function is going to receive the input files. So it's going to be OS args from second one onwards, and it's going to return the master. I'm going to put the function here. It's a list of the path to those input file names, and it's going to return the master. Actually, I'm going to rename this to input files. So I'm going to initialize a pointer to the master struct. And so the next step would be to create the map and reduce tasks. But remember, for us to understand how many map and reduce tasks we need, we're going to need to configure the variables, which is number of map tasks and R is number of reduce tasks. And because we're going to need the M and R later on in the worker, we're going to create them in the util. So I'm going to create another files, and I'm going to call it config.go. Going to be package utils. It's going to first of all define 2 default values for M and R. So it's going to be default. We're going to set it to 8, and default R, we're going to set it to 4. And then I'm going to just create 2 similar functions. This is going to be number of the map tasks. I'm going to need the same one for number of the reduced tasks. And we're going to then provide this M and R variable as environment variables. So we're going to need to read them from the environment. If they don't exist, return the default M and R that we defined. And otherwise, if they exist, then we're going to turn them into integer and return them, because their environment variables read are in the type of string. So I'm going to create a function and call it environment int, which is going to receive a key, and default, which is going to be an integer, and I'm going to return an integer. All right, so we're first going to read that environment using getemp environment variable using the getemp from the OS package. We're going to try to read the key. So if this string doesn't exist, we're going to just return a default. Otherwise, we're going to try to convert this string into an integer. And remember, we're going to use this string converts a to I, which is a string to integer converter. So I'm going to just steer I to a of s. And here, if there was no error, the value that we're reading are greater than 0, meaning it's a positive, because M and R need to be a positive number. We're going to return that value. Right. So otherwise, we're going to return a default. So we're going to use this method that we define in the get the map task and get the reduce task. So let's say it's going to be MapReduce M for the get the number of map task, and the default value is going to be default M, and the reduce is going to be MapReduce R, default R. Right. So let's go back to our MapReduce master now. So now let's try to create the map tasks. And remember, the map tasks, the number of the map tasks should be the number of M, and we want to make sure that we will divide our input files so that we distribute input splits to those evenly. And for that reason, I'm going to create another function. I'm going to call it build map tasks, which is going to receive the input files. And also we're going to give it the number of map tasks. It's going to define this method here, build map tasks, going to receive the input files, which is a list of string and which is an integer. And we're going to return a list of tasks, which are the map tasks. So it's going to be utils task. So to calculate how many splits of the input files we're going to need, one way we can achieve that is to calculate the total size of the input files and then divide it by the number of the map tasks, and that's going to be the target split. So we're just going to sum all of the sizes and divide it by m. So for that, I'm going to create a slice of integer 64, which are going to be our sizes. And this is going to be, the size of this slice is going to be like the number of our input files. And then I'm going to try to calculate the total. So this is going to be an integer 64. So what I'm going to do is that I'm going to iterate over every single input file that we have. And for any of these input files, I'm going to try to get the info using the OSS stats. So this is going to return the statistic of the file. So if we couldn't get this, we have to exit from the program. And we're going to put the input file in the error. Yeah. And then we're going to try to add the size to that index in our sizes slice that we just initialize, and also add that size to the total size. So our target's going to be basically this total divided by, we're going to need to turn the to int64 because total is int64, but because this number might be less than 1, we want to be able to get the bigger number. So make sure we never go less than 1 for the targets. So now that we have the desired target size for each chunks, we're gonna need to calculate what's the starts and the end positions in that input file is gonna be. So I'm gonna first of all initialize a variable for tasks. Then I'm gonna iterate over every single input file. So we're gonna try to open the file first. So we're going to start by defining the start, which is a 64-bit integer. And we want to continue until start is less than the size of that file, because we never want our start to pass the size of the file. So I'm going to start a for loop, which is basically a while loop here until the start is less than the size of this file. And remember, because we didn't change the order of the files, the indices here and here are going to be equivalent. So the size of this index is going to be equivalent of what we actually initialize. So here, one thing that we need to take care of is that we never want to split a line in half. So we have to always snap end of that line. So the sizes are not going to be necessarily equivalent, but as a result, we're never going to split from middle of the line. So to get the end, I'm going to define another method. I'm going to call it snap to new line, and we're going to give it the file. We're going to give it the position, which position is going to be the start plus the target size that we want to go, and we're going to also provide it with the size. So I'm going to define this method over here, and again we're going to provide it with a file which is of type OS file, and the position size, which are both 64-bit integers, and we're going to return the end, which is also 64-bit integer. So here, if this position is greater than size, meaning we are passing the size and we want to return the size. So if position is greater than size, we're going to return this size. So we're going to first of all start by setting our offset to the position. So we read from that offset, and for that we're going to do f.sig and set the offset to position, and we're going to start from the start of the file. So I'm going to set the events to start, and it's going to return error. So okay, after we have our offset set to the position, we're ready to read until a new line delimiter, and we're going to read one chunk, and it's going to be buffer IO. We're going to create a reader for this file. I'm going to read until the byte that we find a new line character or rune. So if error not equal to null, error not equal to IO end of the file, so log the vector cannot read split boundary. So it's going to be read bytes, not just a byte. So after we have the chunk, we can add the size of that chunk to our position, as our position is going to be equal to the length of the chunk. But I believe this is going to return integer, so we're going to turn it into a 64 byte integer. And again, we want to make sure we're not passing the our size. So I'm gonna use min and return the minimum between position and the size. So all these functions is doing is making sure that we always snap to the end of new line. So we're not in a situation that we split the line from a half. So after we have the start at the end, we can create the task and append it to the task slice that we created here. So for the ID, we can use to be incremental, we can use the current length of the tasks, because on every iteration we're adding 1 to it. The status is going to be idle because the task is not started yet. So utils idle. The function type, of course, this is map function. The input address is going to be the F, so that file name that we are currently iterating over. The input offset is going to be the start, and the length is going to be end minus the start, which is the end index and the start index. And yeah, we're going to continue this loop until we hit the size. So we're going to set the start set to the end to go to the next split. So we're going to make sure to close this file afterwards before we open in the next one. So we're going to be file.close. We're going to need to return the tasks. So we're not initializing here. I have to do this. Yeah, so this is going to be our built map task. So to recap, here we start by calculating the target size for each split, which is we calculate the total size of all of the input files and divide it by number of the map. And then we're going to try to create map task by iterating over every single input file. And for every single input file, we calculate the start and the end index, and we make sure that the end index always going to be after a new line. So we don't split a whole line at the end, and we appending the task to our task and returning it at the end. So let's go back to our master now. So the build map task going to return a list of the map tasks. We're going to need to iterate over every single one of these tasks and add it to our map task. So our map task is going to be pending of this task. So it's going to be a pointer to it. So let's go ahead and also define the reduce task. So reduce task, we're gonna basically, it's gonna be the number of the R. So we're gonna just run a loop with I initialized to 0. That we're gonna use this I for the ID. So I is less than getting the number of the reduce task that we define I++. So dot reduce task is gonna be pending reduce task pointed to a task that we create here. So the ID of the task is going to be I, and the status going to be utils idle. The function type going to be a reduce function. And so the rest of the things like the input address, the start index and end index are not applicable to the reduce tasks. And later on, when we get the result from a map task, we're going to set it to the map outputs, so that this digit going to be input after reduce. Reduce going to wait until all of the map tasks are going to be finished. So after we create it and add this map and reduce that to the master, we can return it. We can return the master, which is again a pointer to the master. So remember, both of our master and worker processes are going to be RPC servers, and they're going to be exposing a number of methods to communicate with each other. So we're going to need to create RPC server for both of these master and workers to listen for the incoming RPCs. And for that, we're going to use the netrpc package from a standard library. And because we're going to using the same code for the server in the worker, I'm going to put it in our utils. So I'm going to open up the util. I'm going to go here. I'm going to create a methods, an RPC server, which is going to get a receiver, which adds any type, and a socket name, which that RPC server going to listen to. And so we're gonna start by registering the receiver, and this might return an error. So we're gonna make our RPC to handle HTTP requests. So HTTP, we can call it. And so then we want to listen on a Unix address, a local socket on this socket name. And so we're gonna make sure that if the socket name exists previously, we want to remove it. So we can just OS remove the socket name. And this is going to return a listener, an error. Doing a bit of error handling here. The socket name listener. Right, so we don't want to block the main thread. So I'm going to spin up Go routine to run the server, and we're not going to pass any handler here, and I'm going to just print f that the HTTP server is listening on Unix address of, and going to be the socket name provided here. So going back to our MapReduce master. So now let's provide the master as a receiver to the RPC server method that we just created, and we're going to need to provide the socket name. So the socket name needs to be also available in the forker, because forker need to know the address of the master to be able to make an RPC call to it. So I'm going to put the socket name inside the utils, and I'm going to call it master socket name. It's going to be a constant there. So let's go to RPC. It's going to be constant. It's going to be set to temp. I'm going to map reduce master. Right. So we're gonna block the main thread. I'm gonna add a done method to the master that until it didn't return true, we want to just continue sleeping for 20 seconds. And if it returns true, we can just print that all the task was completed and we're just exiting. So we can just print line. So let's define the done method over here. And let's return false for now. So it's gonna return a boolean. Yeah. Okay, now our master needs to expose two methods over the RPC, one for other workers to get the task and the other one for workers to report they completed the task. So let's go ahead and define those RPC methods. So we're going to receive the arguments, and I'm going to put the argument is in a utils, but let's say it's going to be get task args. I'm going to reply, going to be a pointer to utils dot get task reply, and error if there is any error. Okay, now let's go ahead and define these two types. So I'm going to go back to the RPC in the utils. I'm going to paste these two. So our get task going to basically expect to receive the worker ID. We're going to need that to store it alongside the status of the task that is in progress, and the reply is going to be literally the task itself. So we're going to just return the task. Another method that we're going to need to implement is going to be completing the task. So since we're here, let's go ahead and implement it. It's going to be complete task, going to be complete task. And the reply, we're going to have a generic OK reply that we're going to need in other places as well. So let's go ahead and use it here. All right, let's take these two as well. So the complete task argument, the worker need to provide the task that they completed. It's going to be a task, and the OK reply is literally gonna be empty. So it's an empty reply. So in the get task, I'm gonna use another method, which is gonna be assign, which we'll define shortly, which will provide it with the worker ID. It should give us a task that we'll set in the reply, and there's going to be no error. So let's go ahead and define the assign. It will be receiving worker ID, which is a type of integer, and going to return task. Okay, so it's going to be a method of the master. Okay, so moving forward, we're going to change the tasks in the master a couple of times, and to make it thread safe, I'm going to create a mutex that will locking before starting this operation. So I just go back to the worker, and I'm just going to create a mutex here for the worker. So first thing we want to do in the assign is to lock the mutex. I think I'll call it, which is not a good idea. So let's call it mu. Yeah. After we're done with the assign, we're going to need to unlock it at the very end of the function. All right. And from here, because we're going to need to assign either from the map task or reduce tasks, it's better to define another method that receives function type and does the assignment rather than just repeating the logic here. So I'm going to define a method called assign from, which we're going to provide it with the map task and the worker ID. And this is going to return the task, okay, which is going to be a boolean. So if it was okay, so we can print that assigned map task. It's going to be a digit to worker digit. It's going to be the ID of the task and the worker ID. This will be lowercase. Also, we're going to need to define another method that check if all of the tasks are done. Right, let's go ahead and define the assign from. And assign from, literally what is need to do is to check if there is an idle task available in the list that is provided. If there is, return it, otherwise return false as okay, which is meaning there's no idle task. So let's just define next to our other help method here, kind of. So going to be sort of tasks that we're receiving. It's going to be a pointer to tasks. They're going to be a list of them, and also worker ID, which is an integer, right? And we're going to return a task and a boolean as okay. So we're going to iterate over these tasks basically, and here. And if task.status is idle, then we can set the status of that task to in progress. We can set the worker ID to the worker ID that is provider, and we should set the started at the current time, right? And then we can return the task and true as okay. And if we hit the end of the loop and we couldn't find the idle task, we have to return a task false, right? So we were using this assign from to assigning the other reduce task as well. Also, since we're gonna need to define a method to check if all of the tasks are done, that we're gonna also need to use that in the assign. So we're gonna define an all done method that also receive the same list of tasks. It will return a boolean which indicates whether all the tasks are done or no. So we're gonna do the same thing here, iterating over all of these tasks. If any of these task statuses wasn't done, we're gonna immediately return false. It's gonna be tasks. Otherwise we can return true, right? So let's go back to our assign method. Okay, so if you're able to, if this was okay, meaning we find the task, we're gonna just simply return the task here. So it gets assigned to the reply over here. If we couldn't find a task, meaning over here we have to return a null task, and the idea of a null task is that it's going to have ID of -1 and it signals the worker to wait a bit longer. So that's useful to prevent workers from constantly make a request in the same interval because there's no task available, so better for them to wait. That's what would be more optimal. I'm going to create a function for the nil task because we're going to need to return it in some other places as well. I'm going to just return a task with the ID of -1. And if there's no task available, we're going to return a nil task. Right. Okay, now let's go ahead and implement the complete task. For the complete task, I'm going to also add a method to the master, call it complete, which receive the task coming from the argument, and yeah, we just return nil as an error. So let's go ahead and implement the complete. We don't need to return anything from the complete. So first of all, we're going to start by locking the mutex and unlocking at the end of the function. Second of all, we want to determine what kind of task is that. So I'm gonna start by assigning a variable to the map tasks, and then I'm gonna check if the type equals to reduce task. So in this case, I'm gonna change the task to the reduce tasks. So basically, the task type is either gonna be map task or reduce task. We initialize the task as map task, so if it was map task, we're not going to change it, but if it was a reduced task, we're going to need to change it. So we're going to need to receive the task here as an argument. Right, so we want to check if the ID of the task provided is valid, meaning that it's not less than 0, it's not a nil task, or the ID is basically greater than or equal the length of our task. Because remember, our ID is set based on the index of the task in the list. So if that was the case, we don't want to update. Otherwise, we want to find that task. So we want to get that task from our task list that we just determined by the ID, which is the index of the task. And here we have to check that task is in progress. So remember that I said if the task was previously set to done, we don't want to update the task because it's already done with another worker. So we want to check if the status of the task is in progress. And also we want to check that the task that we find is indeed was assigned to this worker. So we're going to check the stored.worker ID is equal to the task.worker ID over here. So if that was the case, we simply want to change the status of the task, set it to done. And for the map task, the results coming in, and also for the MapReduce task, we want to update the result coming in from the map outputs to the result coming in from the task. So that's going to be our complete function. Again, all we're doing, we're finding the task provided by the completes. If it was in progress and the worker was right, we're setting the status to the done, and we're setting the map outputs to the provided map outputs by the task. Okay, now let's go back to our assign function. And over here in assign function, so we assign the map tasks, but we never assign the reduce tasks. So let's go ahead and do that. Remember, to start assigning reduce tasks, we have to first of all wait for all of the map tasks to be completed. So I'm going to use the all done function that we created, and we're going to provide it with the map tasks. So we're going to only pass this if statement if all the map task was completed. So now what we want to do for the reduce task, we also need to provide the address of all of the workers that we have the map task result in their local disk. So what we need to do, we can just call the assign from the reduce task with the reduce tasks and with the worker ID that is provided, and get the task and also the ID okay, meaning if the task was provided. If we have the task, so this okay, going to be true, we're going to need to add all of those worker addresses to the map outputs. So I'm going to define another method. I'm going to call it map worker locations, and basically here we find the task and the return it, and I'm going to also do the same logging print, which I'm going to say info signed reduce task d to worker d provided with the ID of the task and the worker ID. Okay, now let's go ahead and create the map worker locations, and it's going to be again a method on the master. So I'm just going to define it over here. Right, so we don't need to provide any arguments, but what we're going to return is going to be a list of the map outputs. So we need to create these locations. So I'm going to create those locations. And what I'm going to need, I need to iterate over every single task. What task? I mean map tasks. And so we're going to need to, first of all, make sure we're not hitting the same worker twice. So for that reason, I'm going to create a scene list, which is going to be the list of workers that we already seen. Not the list, but a map from the worker ID to a Boolean. So if we didn't see this worker yet, we're going to add it to the scene list first. And then we're going to append to our locations the map outputs. They're going to be the map output. We're going to have an address here. Basically, we need to provide an address. So the address is going to be the address to the Unix socket of the worker. So let's go ahead and define methods that then we later going to use to get worker Unix address. So it's going to be in our utils. I'm going to call it get worker socket name, and we're going to need to provide it with the worker ID. So I'm going to just provide the worker ID here. So let's go ahead and define this. I'm going to go back to our RPC, just underneath the master socket name. I'm going to create a function actually similar. I'm going to call it sock name, which is going to return a string. I'm going to get the worker ID as an integer. So we're going to literally return a string. So I'm going to use the sprintf. I'm going to need MapReduce worker with a digit. Going to be a worker ID. Right. And let's go ahead and correct this name over here. And so again, what this method does is it will return all of the map outputs, which going to be includes the address of the worker that have the map results or the outputs. And that is needed for the reduce, because they're going to need to fetch that result before they pass it to the reduce function. So we're going to need to return all of these locations now. So our assign will assign a map if there is a task available. If there was any map task available, we're going to go inside this statement over here, and basically all of the task was done. We're going to return a reduced task, and after all of the reduced task was done, we're going to only return nil task. All right. So now that we have this map and reduce task assigned, we also want to make sure that these tasks are not lasting forever and they're completed in a certain time. So we're going to need to define a timeout if any of these tasks wasn't able to be completed, or we're going to need to change the status of that task from in progress to idle, so they'll be reassigned to another worker. So let's go ahead and define two duration in our master. I'm going to call them task timeout, which is going to be of type duration, and we're going to have also interval, and there's going to be the interval where we check if the timeout was hit or no. So when we're starting our worker, we're going to need to start a requeue loop, which I'm going to just define. I'm going to start first calling it. Right. So I'm going to define this requeue loop over here, which is going to be a method on our master. So we're going to run while loop over here. Actually, we don't want to run it on a main thread, so we want to spin up a Go routine that call this anonymous function. And in this anonymous function, we want to run our for loop because we don't want to block our main thread. So we're going to sleep for the interval that we just defined, and then we're going to call another method that I'm going to call a requeue stalled, which is basically queuing the in progress task that hit the timeout. I forgot to define these interval durations, so I'm just going to quickly do that. So for task timeout, I'm going to set it to 10 seconds, meaning that the task needs to be completed in 10 seconds. And for check interval, we're going to set it to 1 second, meaning every 1 second we're going to check that task got completed, right? So let's go back here. Let's define this method. So this method will be run in a Go routine. So we're going to need to create another thread over here. So yeah, let's go ahead and lock our mutex. And this was the reason that we created mutex, because we have multiple threads changing our task store. So yeah, we're going to just get now, and then we're going to need to iterate over all of these task groups. So we're going to merge all of our tasks. So it's going to be a utils.task, and I'm going to put both of our map task and reduce task in a nested loop, right? And so for every task in these groups, we want to check if the task status is in progress, of course, and if we hit the timeout, so we can subtract the started at time from now and see if it's greater than task timeout, meaning we hit that timeout. So I'm going to just print that recurring stale task this from worker this after this amount of time. Break this down. So it's going to be task ID first, worker ID, and the durations. We're going to need to run the subtract again. So we're subtracting from the start to that, and then we're going to round it out to the second. More human readable. Right, so then we're going to change the task status to idle, and we're going to set the worker ID to 0 because we're going to unassign it from that worker. So we're calling this a start and requeue loop. As soon as we create the master in a new master, it's going to spin up a routine that in this interval that we define, which is 1 second, we'll check whether any of these tasks hit the timeout. Okay, so that was all the code that we need for the master. And so let's go ahead and just run it quickly to verify everything is okay. And we'll go run MapReduce master. And remember, we have to provide the input files. And yeah, so the master is listening on this Unix address, waiting for the workers. So let's go ahead and implement the worker. So let's go ahead and create our MapReduce worker. So we're going to start up by loading the map and reduce functions as a plugin. So I'm going to do some argument checking here. Create an entry and here. this. Otherwise, always exit. So we're gonna need to create a worker. I'm gonna use a function provided with the plugins that we will load in the new worker function. Then we're gonna, so let's go ahead and define a worker. So we're gonna need again mutex because we'll be changing the partition files. So there's going to be an ID for the worker. We're going to have map function, and the function signature would be string, and we'll return a slice of key value. And we're going to have reduce function, string, load up the values and return the reduce results. We're going to have number of reduce. So this is going to be integers, and I'm going to have the partition files. It's going to be nested list of strings. So this partition file, those intermediate key value pairs that are returned from the. So let's go ahead and define the new worker function. So we're going to need to provide it with path to the plugin, and we're going to return a pointer to the worker. So map function are going to be loaded from the using this load funcs plugin that we just defined in our for a simple MapReduce. The number of reduce going to be number of reduced tasks. Then we can just create the worker. So the ID would be, so we're going to use the process ID of the worker as the ID of it. That's gonna, because we're running this on the same machine, so that's gonna guarantee that this ID is gonna be unique. Map function is the one that we define here, and reduce function also. Number of reduce, and the partition files, we're just gonna initialize that. And gonna be number of reduce. So each partition is associated with one of this reduce. So after having the worker created, we're gonna again need to run RPC server, because workers need to talk to each other to be able to pull the map task. So we're going to use the RPC server that we defined. I'm going to provide it with a worker, and also we can also provide it with a socket name for the workers, which is literally coming from need the ID of the worker to be calculated. So after that, we need to run the worker. So I'm going to define another method on the workers for running it. Okay, let's define a run for the worker. So in a run, we want to, in a for loop, keep calling master for the MapReduce task. And if there was a task, we want to register them to run them. So we're going to need to define a pull interval in which we're going to run this loop. And also we're going to need to define a number of allowed misses. So if master went offline, we don't want to keep calling it, and we want to have a threshold for it. So I'm going to define two constant here that we can use for this purpose. So I'm going to call out the pull interval, which is going to be 20 milliseconds. I'm going to also have max the all misses set to 100. Okay, so we're going to start by initializing the misses to 0, and we're going to have a boolean whether we connect or no. So I'm going to initialize from false. In a for loop, I'm going to initialize the reply from the master, this is basically get task reply. So we're going to initialize the argument to make a call for the get task. The only thing we need to set from the worker side is going to be the worker ID. And then we're going to try to make RPC call to the worker. For that, we're going to need to define a RPC call methods, and I'm going to put it in the utils because we're going to need it in other places. So I'm going to call it RPC call, which is going to expect to provide it with a socket name that we want to make a RPC call to, the RPC name, which is the name of the RPC method that the server exposes, a set of arguments, which is going to be any object, make a interface here, and a reply, which is also going to be any object. And it's just going to, if there was error, we're just going to return it. So we're going to try to dial with the RPC method, RPC package, make a HTTP dial on a Unix address to the socket name. If there was an error, I'm going to return it. We want to make sure that we close the connection at the end of this function. Yeah, then we want to try to close. We want to try to call after we got connected to the RPC name and provide it with the arguments and the reply. And if there was an error from this, we're going to just return it. So I'm going to use this RPC call method that we created. Let's go back to run. So this is going to potentially return an error. So we're going to get this RPC call is destinated to master. So we're going to use the master socket name. The RPC that we're going to use are going to be get task. And this is basically, if we go to master, we can see that we define the get task over here. So this RPC name is equivalent to that one. And for the argument, it's the argument that we define. And for the reply, we're going to send a pointer to the reply that will be modified. So if this is going to return an error, so I'm going to handle it here. Yeah, so if error wasn't nil, that means we couldn't make an gRPC call. That should be utils standard error. So we're gonna check if we are not connected. We're gonna need to sleep for the interval, full interval time that we defined, 100 milliseconds, and continue this loop. So we're gonna exit out this loop and come back to it again. So if misses was more than the max del misses, we wanna basically exit out, because that means that master is out and we want to exit from the worker. So master is unreachable, worker the exit. I'm going to print out the error worker.id and I'm going to use a return out from here. So returning from here is going to free up the main thread and the program can exit. So otherwise we want to basically wait. We need to increase the misses here. So I'm going to also increase the misses by 1 before doing this comparison. Otherwise we have to sleep and we have to continue this loop. So if we were able to connect, meaning there was no error, we're going to set the connector to true. Misses going to be restarted to 0. Then we're going to basically try to get the task from the reply that we initialized. So I'm going to get the task and we're going to run a switch case statement on this. We're going to compare, we're going to see what type of task it is. So remember, if the ID of the task was -1, meaning it's a nil task, and we have to wait. So if I'm checking the ID here. If the task type was map type, so we're going to check. We're gonna define another method on the worker to run the map task, and if it was reduce task, t.type equals run reduce. Right. So we're gonna need to define these two methods. So let's start by defining the run map method. It's gonna receive task, which is the map task. So let's do a bit of logging here. Let's put the worker ID, task ID, and also the input address. So then we're gonna need to execute the map function and get the key values. So key value is going to be run the map function provided with the input file, and then we need to read that split from the input file. So I'm gonna create another function and call it read split. Let's define that function over here. Receive a task and the input. I'm gonna return a string, which is that split, a read and a stringified. So let's open up the file. I wanna make sure that we close the file. We're gonna use the read add method from the function. So the read add will read length of the byte from the byte slice that we provided, started from the offset, which is the second argument. So we're gonna need to create a byte slice. The length gonna be the input length, pass it to the read add, and the offset is gonna be input offset. So it's gonna return an error. And at the end, we wanna just stringify the buffer and return it. Let's rename this to read split. So remember, we wanna get the results of the key value pairs from the map function and write it to a partition in a disk. So I'm gonna create a bunch of partition. I'm going to call it buckets. It's going to be a nested list of the key value pairs, the number of the reduce functions. Then we're going to need to iterate over every single key value pairs and add that to that specific partition in the bucket. So we're going to need to calculate the partition. I'm going to create a method for it. Then I'm going to define when partition is going to get the key and the number of reduce, and whatever came out, we're going to append that key value to it. Right, let's create the method. We're going to receive the key as a string, a number of reduce files as an integer. We're going to return an integer. So we're going to use the fnv 30 bits hash function that is available in the Go standard library. We're going to write the key byte slice to the hash, and then we're going to get the 32-bit sum modulus n. So this is a formula that we saw in the diagram to calculate the partition. Right, after we have all of the partition, we want to flush them to the disk. So I'm going to create another method, call it flush partitions. I'm going to accept the task ID and the buckets. And at the end, we're going to need to complete the task. These two methods we have to implement. Let's start by implementing flush partitions. We're going to receive the map task ID and the partitions or buckets. So we're going to iterate over every single partitions. If there was no key values, we just want to continue the loop. Otherwise, you remember, we're going to sort the intermediate key value pairs for a bit of optimization. So that's the place we're going to do the sort before flushing to the disk. We're going to use the sort slice, give it the key values and a function which receive I and j, which are integers. I'm going to return key values i.key. So we're sorting by key. Then we're going to create the intermediate key value files that we're going to write to. So the name of the file is going to be MapReduce intermediate. I'm going to put worker ID here, map task ID that we receive as an argument, and the partition. They want to create a file. Right, now we want to write any of these key value pairs as a JSON line to the file that we created. So we're going to initialize a JSON encoder. This is going to receive a file that I'm going to write to. So now we're going to iterate over every single key value pairs. I'm going to write them to the file. So this might return an error. After we're done, we're writing all of the key value pairs. We want to close the file. Now that we have the intermediate file with the key value pairs written to it, we want to add it to the partition files that we have on the workers. But before that, we want to lock the worker and then unlock it. We're going to lock the workers here. I'm going to append the file name to the partition files, and I'm going to unlock the worker. Right, so we flushed all of the partitions to the disk, and now let's go ahead and implement the complete method. So for the complete method, basically we want to make an RPC call to the master and just report that this task was completed. So let's implement this method over here. I'm going to receive a task that is completed. So we're going to initialize the arguments of the complete task RPC, which is only the task. I'm going to make an RPC call by using the function that it created. It's going to call the master socket name, master complete task RPC name and arguments. And because the reply is empty and we don't care about the replies, I'm going to just give it okay generic reply. Let's do error handling here. So if the result was failure, we don't want to fail, but we just want to print the info statement. And the reason is that after the task hit the timeout, the master is going to change the status and try it on another worker or the same worker anyway. So we don't have to waste the results of all of the tasks. I need to initialize this. Let's fix the typo here. Okay, now back to our run function. Let's go ahead and implement the run reduce function. But before we implement the run reduce function, remember the reduce gonna need the result of the map task, which at a moment are stored as intermediate key value pairs on another worker local disk. So we're going to need to first of all fetch those results from that worker local disk. So for that reason, we have to implement RPC methods that the reduce worker can reach out to and get the map output. So let's go ahead and implement the get map output RPC method first. So I'm going to put it right underneath the run. So we have to define a new set of arguments and a reply type for it. I'm going to call it get map output arguments, and reply is get map output reply. Right, let's go ahead and implement these two argument and reply type. Go into our RPC. It's going to create these two struct types over here. So the get map output arg is going to receive a task. And as a reply, we're going to return the list of key value pairs as a response. So back to our get map output. So in the get map output, we want to first of all get the list of all of those partition files that we want to read from. So we're going to start by locking the mutex because there might be another thread that's writing to that partition files. So lock the threads. Then I'm going to initialize the variables, which are the list of the files. We're going to need to do a bit of argument validation here to make sure the partition is actually valid and is in the range. So we're going to get the partition from the arguments ID. So we're going to make sure that partition is greater than 0 and less than the length of all of our partition files. So this is going to be an and over here. So if that was the case, then we can add this partition to our list of all files. And we're going to need to spread it because this is the nested list. After that, we can unlock the mutex. So right, remember when I was presenting in a diagram, I said that we don't want to load all of these key value pairs in the memory, and instead we want to stream them. So we want to create a list of sources instead of reading the entire thing, the entire content of these files in the memory. And for that, let's first of all create type, which define our key value source. So I'm going to scroll down to the bottom here. So I'm defining the key value source type here, which is going to be a function which returns either a key value or a boolean, and second one is basically indicates whether the key value source is finished, we return the last element or not. So this key value source is gonna pulls the next key value from our sorted run and return false when it's fully drained. Okay, now let's go back to our get map output and let's initialize the sources. So we want to create a source for every single file. So let's iterate over the list of the files. We want to open the file. We want to return the error if it wasn't nil. We want to make sure we close the file at the end of this function. So the source that we're going to add to our list of sources is going to be a decoder source. So let's go ahead and create a function that's return this decoder source function. But let's just add it here to the list. So I'm going to append it to a decoder source. It could be a JSON decoder because I remember we wrote those key value pair lines as a JSON lines. So now decode them using the JSON decoder. So let's go ahead and define the decoder source. So decoder source is a function that returns another function of the type of a key value source that we just defined. So we're going to receive a decoder, which is a pointer to a JSON decoder. I'm going to return a key value source. So we're going to return a function. It's an anonymous function and return type should matches the key value source. Right. So we want to initialize the key value that we want to return. So I want to make sure that our decoder can decode this key value and write it to the key value variable that we initialize. initialize. So I'm going to pass a reference to the key value. So if we had an error here, we're going to return an empty key value and return false because the list is not finished yet. So we go to the next element. So if we actually hit actual error, we're going to fatal F and exit. So we're going to just print out the error and exit. And otherwise, we have the key value and we're going to return it. And here we hit the end of the file. So to recap, the decoder source turning a file or intermediate key value file into a lazy reader. We're using the decoder that we provided. It's trying to read the next key value pair. And if we hit the end of the file, we're going to return false as okay, which is the second element, meaning that the file is finished. And if not, we're going to return true with the key value pair, meaning that we still can continue. Okay, now let's go back to our RPC call, the get map output, and we have the list of all of these sources and we're ready to return them. But before we return them, we have to merge all of these sources together. And remember that we done a small optimization that we sorted these individual sources after the return from a map. Now here mergings can be more optimized. We can use something like multiple way merge or k-way merge algorithm implementation and we're going to use priority queue or minimum hip that return the head of any of these sources at a time, and then we merge them together that way. So we're going to run this to k-way merge that I'm going to define afterwards. We're going to pass it the sources, and this k-way merge method is going to return one head at a time. So that head is going to be emitted to this function that is going to be the second argument. It's going to be key value, which is of key value pairs. And we want to get that key value and add it to the response in the reply. So we're just appending that key value to the response in the reply, and there's going to be no error. So now let's go ahead and implement the k-way merge. So let's go to the bottom. Let's implement it here. So we're going to receive the sources as a key value list, key value source list, and also the emit function that we need to call. So like I said, we're going to use a minimum hit for our implementation. So I'm going to initialize the heap over here. It's going to be merge heap. So heap implementation is not really in the scope, but so I posted a bunch of code here, which basically is a heap. So we have the key value itself and the next element, and our merge heap is going to be a list of the merge items and a bunch of methods to get the length, to understand whether one is less than the other, to swapping one item with another, to pushing elements, and from the minimum heap. So we're going to loop through every one of our sources, and remember every one of those sources is going to return the key value and the next. So we're not going to need the key value, but let's get the next. So we're going to get the key value and OK from this next and try to push it to our items or our heap. And we're going to use the continuous heap package from the Go to do the push. So the key value is going to be the key value that we just got, and next is going to be the next one. So this typo here is going to be merge heap with the uppercase H. So here so now we have to find an item or a head that we will return. We will emit our emit function using it. So we're going to continue until we have the length in the heap. So item is going to be the head. So we're going to hit the pop, and we're going to cast it to be a merge item. We're going to emit our function with it, actually the key value of it. I'm going to provide the H heap here. Also, now we're going to push the key value to our heap. So there is a typo here. This is actually a function. So again, to recap the k-way merge, we use a minimum heap. We first of all put all of these sources into the minimum heap by pushing the elements into the heap. And remember, every single one of these items are sources, so we can just merge them into minimum heap. And then we get the smallest element from the heap and return it one at a time until the length of the heap is coming to the end of it. And the way we return that is by emitting it to this function that are provided as a callback. Okay, now let's go back to our run function again, and we can now finally implement our run reduce. So I'm going to put it right underneath the run map. It's only going to get the task. Put a logging here. So we're going to start by getting the sources from the RPC collect that we created outputs. So initializing the sources. So for every single map output that we have in the task, initializing the reply, which is the get map output reply, initializing the argument, which is the get map output args, providing it with the task, making the RPC call here. We're going to need to provide it with the address of the worker that coming from the map output. The method name, which is on the worker, is get map output. This is the RPC method name. Pass the arguments and a reference to the reply. This might return an error. We need to kill the worker if this was error here. So we couldn't fetch the partition. This error nil, provided with the task ID, the address that we're trying to fetch from, and error. And then we're going to add this source coming from the reply to the sources. But because we're going to run the source in our k-way merge, we're going to need to have a way to turn it into the same interface that we implemented as a type in the bottom, the key value source here. So I'm going to create a function that turn it into a function that return that. So we're going to call it a slice source function. I'm going to provide it with a reply here. So let's go ahead and create the slice source function. So our slice source function is going to receive the key values, which is a list of key value, and return the key value source. So I'm going to initialize an index here. I'm going to return a function. So we're going to increase our index until we hit the length of the key values. If we hit that, we're going to simply signal that the source is finished and but return it OK as false. Otherwise, we're going to get that element and return it. Increase our index and return the key value that we find. And also true to go to the next element. So again, returning the result coming from our network call to the same interface that we had for reading the intermediate key value pairs. So we're gonna now create an output file that we want to write our reduce function output to it. And remember to do a bit of failure handling here, where two reduce function write into the same file. We're gonna write the result to a temporary file and then rename it at the end. So the name of the temporary file is going to be, we'll call it MapReduce out with task ID. We're going to go ahead and create the file. We are handling here. Now we're going to initialize writer to our file. I'm going to call it writer is a new writer is going to be to the file. So we're going to use our key value merge to get the head again from the sources that are incoming, that from the slice sources that we created here. And it's going to return the smallest source at a time. So when we get the results, we can write it to the file, and we're going to need to create a temporary emit function here that basically write the results to the file. But also we can be a little bit smarter and write them as a group. So the emit function, we want to get all of the groups and then only emit the groups. So I'm going to call the function emit group. So we're going to create a boolean here that indicates whether we have a key or not. So only if we have key, we're going to write it to our output file. So we're going to use our buffer writer that we initialized. The output format is going to be the same as our simple MapReduce implementation. It's going to be value space value new line. We're going to also need to initialize our current keys and current values. Current key is a string and current value is a list of a string. So I'm going to break this down. So let's write our current key, and we're going to need to return. We're going to need to pass the current values to our reduce function that I loaded from the plugin before writing it to our output file. So we're going to get it from the worker that we initialized, provided with key, and provided with current values. Right, now that we have this emit function, we can go ahead and call our kv merge with the sources. So we're going to provide an emit function. We're going to provide us with the key values one at a time. So we have key, and also the key value key is equal to our current key. We're going to add the current values to our current value list. So we're adding the value to the list of our current values, and we can return from here. And then we want to emit the group with this case. So this is going to be current value. And because it's in the same scope, the current values, current keys are in the same scope as is emit group, it can pick it up. And after we emitted to the keys, meaning we need to go to the next key, we need to reinitialize all of our current key, current values, and have key. So I'm going to do it in one line. It's going to be current key. So basically we want to only have the current values in our current values list. So one way we can do it, we can just append here and only empty out the list and only add this value to it, and true as our have key. And at the very end, when we hit the last items, we want to also one more time call the emit group to have all of the groups. Right, now we have to flush the buffer writer to write all of this value that we wrote to it to the file. So this might return an error. After that, we can close our output file. So now we have to rename a temporary file that we created and turn it into actual permanent output file, which is the output of our entire MapReduce. This is a specific reduce function. So we're going to run os rename, and then the new name going to be MapReduce out, and we're going to put the task ID here. This might return an error also. So after this finish, we want to complete this task. So we can just call our complete function with the task. Right. So to quickly recap, in the reduce, we first of all get all of the sources. We turn them into the sources type that we created using the slice source. And the reason that we wanted later on provided to the key merge. So we created a temporary file to write this result to, initialize emit group that we can group all of the similar keys together and write the same values all together to the buffer writer which is temporary file in this format, which is in a space in between and a new line at the end. Running our kv merge, getting one head at a time, adding it to the current values, and whenever the key changes, we want to emit the group, which basically write into the output file, and at the very end we do it once more time, and then renaming that file. So that's basically dealing with the failures, dealing with the race condition that we talked about during our presentation. And at the end we just complete the task. So that should be our run reduce. Okay, now with that, let's go ahead and run our worker. So I'm going to open a terminal, go run MapReduce worker, and we're going to provide it with the plugin, and it's going to be the work counter functions that we just implemented. So it's listening on a unit side. Let's 1000. That doesn't seem correct. So there should be some problem in our Git workspace socket name that we provided with the ID, and the ID that we set here. Yeah, so the problem is here. We set GUID group ID, but instead we should set the process ID. So I'm going to change this to process ID. So let's try to rerun this. And yeah, this is the process ID of this worker, and we can just open another terminal window, and we can run this command again. And yeah, there's another process. So we can spin up one of these workers, and each one going to listen to on a different process. Another problem that I just noticed in our code is in the master. So we forgot to implement the done method, which is always returning false here. So we never implemented it. So basically in a done method, we just want to check all of our map and reduce tasks are done. So we're gonna start on by locking the mutex, so no one changed the map and reduce task, and then we want to unlock it at the end of this function. I'm going to return that all done map task and all of reduce task. So this is correct. Okay, now here to test our program, I wrote a small bash script that spin up 3 workers. So first of all, we can provide it with a plugin, a shared object. If not, it's going to pick up the word counter function that we built previously, and it's going to spin up 3 workers with that plugin. We're going to store the process ID of those workers. Then we're going to run the map, the master, with all of the input files that we have in the input, which are the input files that we saw with the simple MapReduce, which are literally a.txt and b.txt. And afterwards, they're going to kill all of the workers. So let's go ahead and run this. Make this bigger. So we can run.sh, and it's been all of the workers that you can see here. And yeah, there it is. Right. Now let's take a look at the output files. So we see 4 output files because the number of the reduce are by default set to 4 and we didn't change it. We see the number of the is 2, 1, dog. So similar, the reduce 2 didn't get anything. Cats and sat are 2. So it seems like the MapReduce is working. Okay, I went ahead and also provided with our initial 0.5 GB input text files and configure it to run with the 40 map task and 10 reduce task with the same word counter functions. You can see there's been generated a lot of intermediate key with the different workers for the different partitions, and each one of these includes those map keys, and they're reduced into 10 files, and we can take a look at the result of these 10 files. That's what is the count of each one of these words in a different text files. So implementing map and reduce itself is not really in the scope of this video, but an example of other map reduce that you can find easily out there and implement and test this framework with it are like things like doing the log analysis, or doing the distributed grepping, or finding the reverse web link, or the indexer that we see in the beginning of the video. So I'd like to draw the boundary between our implementation and real distributed map reduce system that runs in a production. So first of all, about the distributed file system and data locality. So I split it a 1 file by byte offset. So a real one schedule each map onto the machine that already holds that data. So the input never moves. In our implementation, in one machine, there is nothing to move. The second point is that in our implementation, we rely on one master. So we keep track of all of the checkpoints and the state of the task in one master kind of process. But if that master dies, all of the checkpoints also gone. So in a real production system, you also want to replicate the master. You want to have a quorum of them that's they sort of agree on a state with some sort of quorum-based algorithm, like a consensus algorithm or something. About the sort that we did for a single partition bigger than RAM, our implementation stream KV merge, which handles big partition, but I never stress a true out-of-core sort, something like external merge sorts. And about the backup task, we kind of just killing the task when they are hitting the timeout, and we retry them. In the real production system, you want to relaunch the last few slow tasks on another machine and takes whatever finishes first. And that's about it. Distributed map reduce. And the trick is that you bring 2 functions, map and reduce, and the framework bring the cluster.